The last part of this chapter is going to cover a little bit about inclined planes and equilibrium forces. So, for an inclined plane, we're going to consider an object that is resting on an inclined plane. In your notes, you should have this arrow drawn straight downward, and hopefully you know that that is the gravitational force or weight vector. And then what we're going to do is break that down into components. So as you can see, I've drawn an arrow that is parallel to the inclined plane itself, and then I've connected that vector component straight down to the end of the weight vector. And so this makes a little right triangle. And then whatever the angle of your incline, that angle is going to be right here as well. And this is going to be called the parallel component of the weight. And it's called that because the actual leg of this triangle that we've made is parallel to the inclined plane. We can do the same thing on the other side. Now we can drop a line this way and draw in a component to a vector that is perpendicular to the incline and create our right triangle here. And this would be the same angle as these other two positions. This vector component that we are drawing is called F perpendicular because it's the perpendicular component to the weight. And notice that we've also had a normal force that was perpendicular to an incline. If we were to draw in our normal force vector, it would be pointing this way, up away from the incline, perpendicular to it. The magnitude of that vector will be the same as the magnitude or size of the perpendicular part to the weight. So that's another way you can calculate the normal force. So how can we figure out the actual size of each of these? So if I consider the portion of the picture on the previous slide with the parallel component, I can look at the sine of the angle would be the opposite leg, which is this one, over the hypotenuse, which would be my weight. So the parallel component is the opposite leg, and then the weight, or the gravitational force, is the hypotenuse. So my parallel component can be written as the weight, or the gravitational force, times the sine of the angle, if I were to rearrange those. And I went ahead and wrote out the entire subscript variable for you for that whole word parallel, but you can abbreviate it. And remember also that the weight and the gravitational force are the same thing, so you Our last section is on equilibrium. You first have a definition of an equilibrant. That is a force that puts an object in equilibrium. And when we're talking about an object being in equilibrium, the most common case would be for all of your forces to cancel each other out so that your object is not moving. And similar to when we studied projectile motion and we separated horizontal and vertical equations and looked at those separately, we're going to do that as well with our forces. So we would take the sum of all the vertical components of a force and add them up, and that would have to equal 0. And then the same thing with our horizontal components. The sum of all of those parts of the forces would also be equal to 0. So you have an example problem where you are asked to hang a 65 Newton sign from two chains that are each 24 degrees to the horizontal. We are interested in how much force is applied to each chain to hold it up. So you've got a little picture of a scenario. These are going to be our chains, and then we know the weight of the sign. So what I did over here was indicate a free body diagram. So I'm going to say that this was my gravitational force, or my weight of the sign going downward, and then chains would represent a tension, so you can do a T or an F with a subscript of a T on each of those. When we go to solve the problem, we're going to refer back to this picture in order to break down our forces into components and actually find out how much tension is needed in each chain. So a couple of things to note when we go to solve this problem. Remember, our vertical components will use sine and the horizontal components will use cosine. So from looking at our picture, we want to recognize that the two horizontal components are going to have the same magnitude. So if we were to drop a line straight down from each of our forces and make a right triangle, we know that this is 24 degrees. And then we can do the same thing on the other side and make that tension into a right triangle, and this is 24 degrees. You should be able to tell from your picture that this horizontal part to your triangle and this horizontal part are going to be the same size, and that's what we mean when we say they have the same magnitude. So these two are going to cancel each other out. When we look at Newton's second law, we would want the sum of our forces to equal 0. So for the object to be in equilibrium, we need this part of tension number 1. You can see from your picture that that would be in the positive x direction, and that this part in your free body diagram, that horizontal component would be in the negative x direction. So if I add those two together, they add up to 0. So that means that our sign is not moving side to side horizontally, that it is in equilibrium in terms of the horizontal motion. The last step is to make sure that the vertical components add up to be 0 as well. Hopefully you can tell from the picture that the vertical component to each of my tensions are in the positive direction, but my weight or my gravitational force is actually in the negative direction because it's pointing downward from where your coordinate system was indicated. So to add up and look at the net force, I would say the y leg of one tension plus the y leg of the other tension, because they're both in the positive direction, and then subtract the gravitational force or the weight. That total has to add up to 0. So what I want to do to calculate how much tension is in each of these chains, if I can figure out how much one vertical component is, and I know the angle, I can use the sine to figure out what my hypotenuse is for one of those tensions. So let's go ahead and solve. I'm going to add the two y's together, and then I'm going to add the w and take it to the other side. So I end up with 2y equals w. Now, if I were to solve for y, I know that everybody knows you end up dividing the weight in half. So if we look at our numbers that were given in the problem, we had a weight of 65 newtons for the sign, and we want to divide that in half to figure out what one of those y legs would be. So that tells me that one of these vertical components, either one, because remember it's symmetrical, either one of those y legs would be 32.5 newtons. Now I can use that information to actually calculate the tension in one of the chains. So if I look closely at that triangle, so let me go ahead and redraw my tension. We know that this angle is 24 degrees, and we've solved and figured out that this leg of the triangle is 32.5 newtons. So now I can use the sine of the angle to figure out how much tension is in that chain along my hypotenuse of the triangle I've created. So I'm going to say that the sine of 24 degrees would be equal to the opposite leg, which is 32.5 newtons, over the tension. And I'm going to go ahead and multiply the tension on both sides just to show an extra step. Algebraically, we want to make sure that we're solving for the tension, and to do that, once we have cross-multiplied, now we're going to divide both sides by the sine of 24. And this gives us a final answer of approximately 80 newtons. So that means in order to support that 65 newton sine, each of these chains on both sides, each one of them is going to have a tension of 80 newtons to support that sine and keep it in equilibrium, which means it's going to be still. In your notes, I believe there's another letter that says, in class we will do problems together where the angles are unequal. We actually are going to omit that section. So you would have to solve a problem similar to this one where we do have the same angle on both sides. So we are dealing with a symmetrical scenario. So this will be one of the math problems you'll see on your test. If you have any questions, as always, make sure you schedule a time to come in and get some extra help.